I have actually a written notes also on this. Uh, if you want, I can share, but you can follow this. Okay, so far we have discussed up to this, isn't it? So far we have discussed up to this. Now we will discuss this one. Forget that. Okay. So we will try to understand this. Try to follow. That whatever I have written, try to visualize this graphically, because understanding graphically is more, I think it is convenient, right? Than understanding is theoretical or analytical. Okay? So we will try to analyze this graphically. What is the meaning of this? Try to understand that when we are actually considering a reacting system or a system in which there is reaction as well as flow, right? A reacting flow system. So you have a combustion chamber in which some reactants, that is fuel and oxidizer, is going, and the product of combustion is leaving, right? Say for example, it can be in gas turbine, it can be in IC engine, whatever, right? So these are the reacting system in which there is flow. In case of gas turbine, it is continuous flow. In case of IC engine, there is intermittent flow. That means there will be some time valve opening, and then there will be internally, that means there will be closed system. Reaction is going on. Then after that, there will be valve opening and the product of combustion leaving. So depending on the system, you can have intermittent flow, you can have continuous flow. In case of gas turbine, it is continuously flowing. Right? There will be compressor, then gas turbine, right? But the thing is that flow system, most of the things are flow system. It can be a closed system also. The thing is that how to analyze. You see that in the last class or in some of our earlier classes, we have discussed that that is total change in energy is equal to what? Total change in energy is equal to what is that? Delta E. This one. Change in energy of the system is equal to change of state and change due to chemical change, right? Change due to chemical reaction and change due to physical change. That means when there is a change in temperature and change in pressure, then it is a physical change. That is called change in energy of the state. When there is a chemical change, that means from reactants to product, that is called chemical change. So total change of the system, that means from reactants to products, there will be a total change due to change in temperature and pressure, and also due to change in chemical composition. So from reactants to products, it is chemical composition. So corresponding change is this one, and from this reactant condition, that is temperature and pressure, there will be also change in temperature and pressure. So total change is this due to both physical condition change and chemical composition change. Okay, so that we have discussed rigorously. Next is whenever we try to understand the enthalpy of a particular, say for example, particular component of the reactants or the products, right? Try to understand the the total enthalpy of the total enthalpy of any component. We try to understand. So how to understand? So we have understood in the last class that there is a concept called enthalpy of formation. Enthalpy of formation. What is that? When something is formed, anything, right? Say it may be oxygen, it may be nitrogen, it may be CO2, it may be anything. So whenever something is formed from its stable element, then we can calculate the enthalpy of formation, right? So that is the idea. So this is this. What is the meaning of this? Can you recall? HF0 bar. What is the meaning? So try to understand that. So just follow this. So this is the enthalpy of formation, and this is the change in enthalpy due to change of state. Change of state. So this is chemical, this is physical. So this is delta E state. Try to make the correspondence between these two. Okay? Clear? Now what is the unit? Kilojoule per kilovolt. What is that? This bar means it is per unit mole or kilomole. Okay, this bar. So bar means whenever we have bar, it is based on moles. Okay? Clear? Now I will just hide it first, then I will write, and then again I will explain. Okay? Try to understand. Say I want to understand. Say for example, if I try to write the reaction, what is that? What is the reaction? Fuel plus oxidizer, product of conversion, right? That is the reaction. Okay. Now, say fuel can be anything, right? It can be hydrocarbon, it can be simply carbon, it can be alcohol, anything, right? Solid, liquid, gas, anything. Next is say oxygen, right? So oxygen or air, whatever, right? Next is we try to understand what is the enthalpy change of this. So far, what we have done, we have tried to understand the mass balance. Mass balance is very easy to understand, right? Because you cannot hide some mass, right? So whatever mass of this is equal to mass of this, right? You cannot hide it. Fuel plus oxidizer. So in case of mass, you don't have any confusion there that there will be some mass hidden, like potential mass and kinetic mass, right? Like that. So something you can always measure. Mass you can always measure, and this is equal to this, right? But in terms of energy, when we actually try to understand that something you can see and something you cannot see, right? So that is how we have to basically understand. Next is that when we actually see enthalpy of formation, how we actually see that. Let us try to see. So this is say enthalpy diagram. What is that? Enthalpy, and this is temperature. Temperature. Okay. It can be enthalpy per unit mole. It can be enthalpy per unit mass. Whatever. No problem. Okay. Next is whenever something is produced, it is produced from something else, right? So for every reaction, you can understand it in terms of some products and reactants. Say for example, oxygen is produced. This is oxygen, right? So oxygen is produced from say 2. So this is a forward reaction. So you can have a reaction like this. O2 is dissociated to 2. 22. Clear? Next is how we can visualize this in the diagram. First one is, which type of reaction is this? Can you tell me? Which type of reaction is this? Endothermic, exothermic? This is what? So bond is formed. So if bond is formed means energy will be released. So it is exothermic. Okay. And this is endothermic, obviously reverse reaction. Okay. So can we visualize the diagram here in this? This is very crucial. If I understand, then it is okay. Then I understand every reaction. If I do not understand, then it will be difficult to visualize the reaction. Okay. So that is why it is crucial. Talking is okay. But if you talk, you will miss this important thing. Okay. So that is your wish. Next is, so if I try to plot this, say for example, I want to plot this, where reactant is this, right? This is reactants. Say, let us give two colors. This is reactants and this is products. I will plot with corresponding color there. This is products. Okay. So at a particular temperature, so this is temperature, isn't it? So if I draw at a particular temperature, say, if I draw at a particular temperature, any temperature. So which enthalpy is more? Can you tell? At a particular temperature means what? Ideal gas. Say for example, this is ideal gas. Okay. Which enthalpy is more? Which enthalpy is less? This is exothermic reaction. So which enthalpy is more? Product enthalpy or reactant enthalpy? Reactant enthalpy will be more than the product, because this is exothermic. Because from this it is spending this energy. Try to understand. Try to follow this. From the chemical energy, this energy, thermal energy is released. That means this thermal energy was there in the form of chemical energy. Now that chemical energy is released in the form of thermal energy. Therefore, this thermal energy was there in the form of chemical energy. So this chemical energy, that is enthalpy related to chemical energy, is more than this. Is it clear? So reactants, chemical energy. You see, this exothermic means thermal energy is released. So thermal energy definitely was there in this, right? So that thermal energy was there in the form of chemical energy. Now at a particular temperature, what is the meaning? At a particular temperature, state condition is 0. That means this delta E state is equal to 0 at a particular temperature. This is 0. Therefore, whatever change is taking place, that change is taking place due to chemical change, right? Therefore, this energy, whatever was there in the form of chemical energy. Therefore, chemical energy of reactant is more than chemical energy of product, because this plus this is equal to this. Therefore, chemical energy of the reactant is more than chemical energy of the products for exothermic reaction, right? So, therefore, if I draw, is it clear to all? So, therefore, if I example, this is the enthalpy of the reactants. This is the graph of enthalpy of the reactants. Okay? Right? And if I draw the enthalpy of the products, why it will be lower? At a lower position. Like this. It may be diverging, it may be converging, depending on at a higher temperature what happens, whatever happens. Right? Okay, clear? Okay. Next question is, this is very crucial. Next question is, what is this? If you once understand this graphical, it will be very clear to understand all the reactions. Okay. So what is this? What is this? That means at a particular temperature there is a change. So when the reaction is taking place, that is the change in enthalpy. What is that? What is that change in enthalpy called? Q is equal to Hp minus Hr is equal to that is called enthalpy of formation. For this particular reaction at a particular temperature, this is, say, for example, this is the standard reference state. Standard reference state. Okay. So this is standard reference state means what? At 25 degrees centigrade and 1 atmospheric pressure. Right? Is it clear? Is it clear? Therefore, what is this? What is this? Are you following? HF not F, right? HF not bar, huh? HF not bar. Clear? This is enthalpy of formation. That means when I subject these reactants, this is reactants. When I subject these reactants at this temperature and pressure, it goes to the products and releases energy. So when it releases energy, its energy decreases. Its energy decreases, and that extra energy is released in the form of thermal energy. Is it clear? Okay, great. Next is, that means whenever we go for such thing, there is a change in chemical energy that is corresponding to enthalpy of formation. Okay. Next is, if in addition to this there is a change of state also, if in addition to this there is a change of state also, then we have basically some change in state. Say for example, change in state means what? Change in temperature, pressure, right? Change in temperature and pressure, right? So it is like this. Say for example, from T to some other temperature. So some T0, this is T0, and this is some temperature T, some temperature. So from T0 to T. Okay, some T0 to T. Now say it is here, or it is here, whatever. That means it is going from this to this, from this to this. So what it will be? This is basically this is h bar minus h0. What is that? H bar minus h0. What is that? What is that? H bar means at this minus h0 means at the standard reference state. So this is basically sensible energy change. Clear? And this is what chemical energy change. Clear? Therefore, if I want to write the enthalpy of a particular component, then that will be enthalpy of any component. For example, atomic oxygen or molecular oxygen, whatever. If I want to write the enthalpy of that particular component, then I will write this change in chemical energy plus change in the sensible enthalpy. What is that? So this is change. Remember that this is HF0 means this is change. This is not a particular condition. It is a change of enthalpy. Clear? So therefore, total enthalpy of any component of the reacting system or reaction is equal to what? HF0 bar plus H minus H0. Clear? So this is the enthalpy for the reaction plus the change due to state. So you see that there is one thing that is during this, for example, 1, 2, 3. So the component is moving from state 1 to state 2, then state 3. So it is like this. This is the process. Two processes are there. So one process is from 1 to 2. What is that? Chemical reaction. Chemical reaction. Next, what is happening? Due to chemical reaction, there is some heat generation, and due to that heat, the product is now heated. So initially, what is happening? From reactants, product is formed. So this is the chemical reaction, and from this to this, the product is now heated because of thermal energy. So because of this thermal energy, the product is heated. So initially product is formed, and then due to the heat generation, this is heated. So 1 to 2 chemical change, and 2 to 3 change of state. Clear? So that is the thing. Clear? Sensible energy change. Okay, clear? So what is this? H. When I write 0 means what? At this T0. So standard reference condition. T0. What is the bar? Bar means per unit mole. And what is F? Formation. Enthalpy of formation at standard reference state per unit mole. Right? Clear? Is it clear? Is it clear? Done? Okay. So E dot in is equal to E dot out. Clear? Next, what is the meaning? That means total energy in is equal to total energy out. When it is true? When it is true? Are you writing? When it is true? When it is true? During steady flow condition. During steady condition, it is true. That is, E dot in is equal to E dot out. Energy in is equal to energy out where it is steady. Right? Kinetic energy and potential energy we are neglecting. Not necessarily. It is true when you have basically steady flow. Steady flow means at the inlet and exit may be different, but this is true. Right? But for your determination of enthalpy of reaction or enthalpy of combustion or enthalpy of formation, you have to ensure that at the inlet and exit the conditions are same. Because you have to equate the chemical energy change, you have to understand the change in chemical energy only, because you have to nullify the condition of state. That is why we are ensuring the conditions same at the inlet and exit, or the reactants and the products. Is it clear? But here you see that total energy in is equal to total energy out. So this total energy includes what? Some chemical energy, some thermal energy maybe, right? And total energy out also maybe some chemical energy, some thermal energy. Clear? So next is we rewrite the first law. This is first law, steady flow energy equation. So Q in plus W in, as if, for example, you understand that this is the control volume in which some energy is supplied in the form of heat, some energy is supplied in the form of work. Then this is what? There are three modes in which energy can be transferred into a system. What are they? Heat, work and mass flow. Right? Try to understand that a system and surrounding can interact in three ways: heat transfer, work transfer, mass transfer. Right? And in all three ways, these are energy interactions. So heat transfer and work transfer, they are already energy interactions. And with mass transfer also there will be energy interaction, because mass can carry some amount of energy with it. Is it clear? Therefore, so we are trying to understand the energy interaction of the system and the surroundings. So during it enters, so it is, say for example, you have a control volume. You have a control volume. So it is energy in, energy out. Right? Energy in can be this, that is mass transfer. Energy can be work transfer, work out, and energy in can be heat transfer, heat out. So 3, that is 1 plus 1 plus 1, 1 plus 1 plus 1. So what is the heat transfer? Heat in, another is work in, another is mass in. So energy traveled into the system in the form of heat, plus energy carried into the system in the form of work, and energy carried into the system in the form of mass. Right? Similarly, this is energy out. Okay, is it clear? Next is internally, is it clear? HF0 plus H0 plus H. This one. I have written on it. This plus this. Clear? This one. So this one. Clear? Okay. So HF, this part is clear internally. Now what is the assumption here? Potential energy and kinetic energy are neglected, because most of the time we consider that the change in chemical energy or change in enthalpy is much more compared to kinetic energy and potential energy. Right? Even if it is not compressible flow, we will discuss compressible flow just after this. That during compressible flow, definitely kinetic energy cannot be neglected, because compressible flow means necessarily there is flow generated due to the flow generated due to the change in enthalpy. So they are comparable. That means from enthalpy you can generate flow, right? So in that case you cannot neglect. Otherwise, most of the situations you can neglect the kinetic energy and potential energy. Okay. So this is the internal part. Okay. Now what is this in dot? What is the meaning of that? In dot means basically mass, the mole flow rate, the flow rate of moles. Okay. And what is the unit? You can just match. What is the unit of HF? What is the unit? Can you recall? What is the unit of HF? Okay. So you see that this is N dot R, means this is rate of net energy, this is net energy and this is mole flow rate of mole. Mole or kilomoles. Okay, so what is the unit? Kilomole per second. Unit is kilomole per second. What is the unit of this? Kilojoule per kilomole. Kilojoule per kilomole. So when I multiply these two, it becomes kilojoule per second. So that is rate of enthalpy transfer simply. That is extensive property, rate of enthalpy transfer. Right. Earlier during our discussion on say that is boilers etc. What we discussed is that it was written in terms of mass flow rate multiplied by H. Right? What was the unit here? kg per second, and this is kilojoule per kg. So here you see that kilomole per second, instead of kilomole per second it is kg per second, and instead of kilojoule per kg it was kilojoule per kilomole, it was kilojoule per kg. So kg and kg will cancel, it will make it kilojoule per second, and these two will make it again kilojoule per second. Both are same, right? So for reacting system, it is always convenient to use kilojoule, that is kilomole, and kilomole, that is kg per kilomole, right? And here it is kilojoule per kg and kg per second, right? Either it is mass flow rate or flow rate of moles, number of moles, right? Okay. Next, another thing is that this is number of moles per second in dot, right? Okay. So this is rate. This is rate equation and this is total equation. If I integrate this over some time, then we will get this. So you see Q dot, here it is total enthalpy, total energy. W dot total work. That means over some time, if I integrate this equation, we will get this. So here N dot R means rate of flow rate of moles, and NR means total number of moles involved for the reactants, individual reactants. Now when I write this summation, what is the meaning? When I write this summation means for reactants. So you may have a number of reactants. For example, in the reactants, what are they? Fuel, then oxidizer, right? So fuel, then oxygen, nitrogen, etc. So for say hydrocarbon, one hydrocarbon plus oxygen plus nitrogen we will add individual, right? And here you have products. What are they? In the products, individually, so CO2, H2O, nitrogen, excess oxygen, etc. So individually, when we basically break this summation, we have basically product of combustion, that means CO2, H2O, oxygen, nitrogen, etc. Okay. So this summation, that means that, right? Clear? So this is the first law. This is some elaborated part. Simply we have added. Now this is a generally what we consider that heat transfer into the system is positive and work done by the system is positive. So Q is the net heat transfer to the system and W means the net work done by the system. So we have added this simply from the earlier page. Q means Q in minus Q out and W out minus W in. Okay, so this is the general convention, and this is what? Sorry, this will be minus sign. Instead of equal, this will be minus sign. So it is basically products minus the reactants. So the energy interaction for the products in terms of mass transfer minus the energy interaction of the reactants in terms of mass interaction. So this is total enthalpy of the products living with the mass, and this is total enthalpy of the reactants entering into the combustion chamber, right? And this is kilojoule per kilomole of the fuel, per unit mole of the fuel we are using. Okay, so that is the final version of the reaction, where you can write H product means this one and H reactant means that one. And finally, enthalpy of combustion for a particular reaction. So enthalpy of combustion for a particular reaction, that means if I just write for a particular reaction, it will be, what is that? This one. Now you see that what is the enthalpy of combustion for a particular reaction? What is the meaning of enthalpy of combustion? Can you recall? Enthalpy of combustion means, when we consider enthalpy of combustion means it is at a particular temperature and pressure. Therefore, this will come enthalpy of formation part, enthalpy of formation part for the products and reactants will come, and this will remain there. Right? So this is HC0 bar. HC0 bar means basically this minus this. This minus this. So that is the total enthalpy change of the products minus total enthalpy change of the reactants when it is considered at a particular temperature. When it is considered at a particular temperature. So this is the enthalpy of combustion. When we consider total products and total reactants, I consider total reactants and total products. It is for a particular component, but if I consider total energy of the products and the reactants, then similar graph can be drawn, and in that case also I can get this as, instead of HF0, it will be HC0, that is enthalpy of combustion. Right? That is the total reaction. That means all the components here, all the components are involved. Try to understand. Here all the components are involved. This means this minus this. So total enthalpy of the products at a particular temperature and pressure, total minus total enthalpy of the reactants at that temperature and pressure, that is the standard reference rate. So that is equal to this minus this is equal to this. And the remaining things are as it is. So just I can write the first law in terms of enthalpy of combustion for a particular combustion reaction. Right? Okay, thank you.